Now, ideally, we would like to have a scanner that gives us an infinite spatial resolution in theory, and we would be happy with such a technique. However, this is not the case in PET, and the question here is, why can the resolution be never perfect? Well, let's look at the process here. We have the positron that's being emitted from the unstable parent nucleus. The positron diffuses, loses energy, and does the annihilation with an electron after a certain distance. And this distance here is called the mean free path length, or the positron range. And this range, there's nothing we can do about it. This range exists, it is there, it is non-zero, so the positron does not leave the nucleus and immediately annihilate with an electron, it takes some distance. Let's give us some idea. In the air, if you have a positron emitter, the positron range is actually several meters, so it is quite long. But if you look now in water, and here I've plotted on this table a number of isotopes. We'll start out with the most ubiquitously used, the fluorine-18. With its characteristics, it has a half-life of roughly 2 hours. The kinetic energy of the positron is roughly 0.6 megaelectron volt, and the range of the positron in water is roughly a millimeter. That's the full width at half maximum, so half of the positrons will travel further than 1 millimeter. If we look at C11, the half-life is around 20 minutes, the energy is higher, it's 1 megaelectron volt, and the range of the positron emitted from the C11 nucleus is a bit higher than that of the fluorine. Oxygen-15, also a widely used tracer, has a surprisingly short half-life of 2 minutes, positron energy of nearly 2 megaelectron volts, and here the range of the positron in water is 1.5 millimeters. Then we have nitrogen-13, 10 minutes half-life, gallium-68, which you can produce in a hospital, 70 minutes, and rubidium of 1 minute. Photon energies between 1.2 and 3 megaelectron volts, and again, the range of the positron in water is around 1.5 millimeters. So these distances, we cannot manipulate them, we cannot improve them. They are there, they are a given, and we have to deal with this imprecision. This basically means that even if we're able to determine precisely the location of a positron and electron annihilation, this does, by 1 millimeter distance roughly, not represent the location of the parent nucleus. So here are the most frequently used isotopes: fluorine-18, C11, and oxygen-15. Now there is another effect, and that is we have assumed collinearity of the photon pair for the reconstruction. So the background of this is that we have assumed that at the time of annihilation the electron-positron pair has zero kinetic energy. Now in reality they will not have non-zero kinetic energy, and we have conservation of momentum to consider. So let's have the nucleus here. We have the positron, it finds the electron, annihilates, and goes up in perfect 180 degrees. This is the situation where the positron and the electron together have zero kinetic energy. In this case, the two photons will be perfectly 180 degrees apart, and we have zero momentum of also the photon pair. Now let's consider a situation where the positron and the electron have non-zero linear momentum. So the positron and the electron, their linear momentum is non-zero. That's indicated by the arrow here. So this is a resulting linear momentum. Now the process of annihilation conserves linear momentum, so the two photons should have non-zero linear momentum. To achieve this we have to imply that the two photons are not emitted 180 degrees apart, but are deviated by a small angle from this collinearity. So we have the two 510 kiloelectron volt photons. They are not perfectly opposed to each other because their net linear momentum is non-zero. So this will now give us a line of incidence that's different we will detect the photon at a different place than where the positron-electron annihilation has happened. This angle is very small, it's 0.25 degrees roughly, so we can estimate from that the error in location. So we'll take the distance delta x here. We'll say we have a detection distance between the detector distance between the two detectors of big D. And so we can calculate with this, we can calculate the deviation of where we detect the photon pair relative to the true location is 0.5 d times tangent of 0.25 degrees. So what does this mean? We'll plot here just as a function of d the position error. We have, if the two detectors are 60 centimeters apart, then with a 0.25 degree angle, we have a error of 1 millimeter. At 80 centimeters, it's nearly 2 millimeters, and 100 centimeters, it's a bit above 2 millimeters. This gives you an idea of the location error. Now, we're assuming collinearity of the photons, so they are opposed to each other outside. If they are not, then we can have deviations from 60 centimeters to 1 meter of roughly 1.5 millimeters. So this deviation can happen in all directions. So this basically just means that we have a blurring of the representation of the position of where the electron and the positron annihilated. This adds on top of the range of the positron. We already have here the range of the positron. That gives us an uncertainty. And then if we have a large detector distance, we have also an uncertainty in determining the location of where the positron and electron annihilated. Now, we have said that the detection of X-rays for positron emission tomography, the methodology that's used, that is scintillation followed by amplification with photomultiplier tubes, is the same as for SPECT. And as you might remember, the photomultiplier tubes have a certain dimension, the scintillation crystal has to have a certain thickness, and this is the question: how does the detector, the choice of the detector, affect the spatial resolution of the positron emission tomography scan? So let's take as an example a BGO block detector. I'm bringing here this example to also put some numbers on the characteristics. The coincidence window that you can choose with a BGO block detector is on the order of 10 nanoseconds. The energy resolution is roughly 25%. So this is to give you some specific numbers. Now, we will look at the true incidence count rate. We'll call that R2, RT for trues, is given by 2 times the tissue radioactivity times the factor, so the CT star is the tissue activity of a voxel. We have epsilon is the intrinsic detector efficiency. It essentially represents the ability of the scintillation crystal to stop the X-ray, the 510 kiloelectron volt photon, and to simplify it, it basically means here the ability to stop them, so it's given by 1 minus e to the minus mu x. The mu, the linear attenuation coefficient here, is that of the scintillation crystal. So ideally we would have a fairly thick crystal, x being high, linear attenuation coefficient being high, and in this case the efficiency would be close to 1. So here's an example of a scintillation crystal here and the photomultiplier tubes on top. We'll look here at a more modern detector here. We have the photomultiplier tubes here. Here's the electronics. Here's the scintillation crystal, and the scintillation crystal has a certain thickness here. We have to consider also the geometric efficiency, that is, what percentage of the solid angle do we see by the detector. So the detector surface here in green divided by 4 pi the radius squared, this gives us the percentage of all the counts, all the X-rays that we can detect. Well, think of it this way: all the X-rays pairs go in all directions. We have a detector up here. This detector will only see a small percentage of the entire spherical surface at its location, and these are the maximum counts that you can have. It's the geometric efficiency. So, to give you an idea, If we look at the intrinsic detector efficiency, if we have the detector efficiency of this detector here, let's say, is 90%, since we are detecting a photon pair, we have to also consider the detector efficiency on the other side. So if each detector has an efficiency of 90%, then we have 81% of the photon pairs that are emitted towards the detectors that produce coincidence. And so this is a reason why we cannot use infinitely thin crystals. We have to use them fairly thick, and the typical dimension here is 3 centimeters. Okay, so if we look at now our detector ring, here's the crystal thickness. We will now look at the detector ring, and we are considering these two detectors here, just opposite of each other. This is the line of incidence that's defined by the two crystals. And if we have an annihilation event here, then we will attribute all the events here on this line of incidence. This is the good situation. We have good resolution. It's the detector width here, the position measured here and here that defines the line of incidence. Now let's consider two detectors a little bit offset on the that are not just opposite each other. We have an event detected in this crystal, and we have an event detected in this crystal. So what does this mean now? Basically it means we can have detected an event anywhere in this shaded area. This will create any event that is in here, or any event that's detected here in this crystal or in this crystal, could have had the annihilation between electron and positron anywhere in this gray area. So as you can see now is as we are getting away from the center of the scanner, the resolution is poorer because of this geometrical consideration. So the take-home message here is, of a standard PET scanner with this technology, the resolution is best at the center of the scanner.